So thank you very much for the invitation and welcome to part 2 of Australia Day at the current developments of mathematics. I apologize for the experts who came to my talk. The first talk is very definitely intended to be a colloquium-style talk. So hopefully some of you will appreciate that. So let's start by taking a polynomial with integer coefficients with no repeated roots. So first, I'd also like to define the quadratic residue symbol, NP. So this is given by 0 if n is congruent to 0 mod p, plus 1 if n is congruent to 1 mod p, if n is a square mod p and x is not congruent to 0 mod p and minus 1 otherwise. Okay, so this is just the indicator function for which numbers are squares mod p. Just to give a very concrete example, so if p is equal to 11, then the squares are given by n that are congruent to 3, 1, 4, 1, 5, or 9 mod 11. Okay. So associated to this polynomial f of x, let me consider the following sum, which I'm imagining p is going to vary. So this is just going to be the sum from n is 0 to p minus 1 of the value of this polynomial at p. So in other words, this polynomial, you run from n to 0 to p. When it's a square, you have plus 1. When you have a minus a square, not a square, it's minus 1. And I get this number, which is in z. Okay, so the first basic lemma, if f of x is just x, then exactly half of the numbers are squared. And so ap is equal to 0, well, as long as p is bigger than 2, which behaves a little bit differently. So the question is, what happens for polynomials of higher degree? So the next natural case is degree 2, but in fact, by a trick, which I'll leave out, for polynomials of even degree, you can always make a change of variables to reduce it to a case of degree 1 less than that. So let me insist that d degree of f is odd. Okay. So this is really the general case because it can always be reduced to this case. All right, so here we have a number. Fn is perhaps to some extent being random. We're adding together these pluses and minuses 1s. So the probabilistic model, or the probabilistic guess, would just be to assume you're taking a random walk, and then you would imagine that this value of AP, normalized by root p, will maybe vary as a normal distribution, perhaps even with standard deviation, what you would expect. I hope that's the right number. Okay, so actually this is a very good first approximation, but it's not quite right because there are extra constraints, of course, coming from arithmetic. So there's a theorem in this case, which is due to Weil, and in fact it's a very special case of the Weil conjectures that were later proved by Deligne. And well, it says you don't quite get this, but it gives you a particular bound, namely that minus 2g is less than or equal to AP on root p is less than or equal to 2g, where g is something that in fact it only depends on the degree, and it's equal to d minus 1 divided by 2. So for polynomials of degree 1, you always get 0, but for polynomials of degree 3 and higher, well, at least this constraint is not giving you anything necessarily that's forced to be a specific number. Okay, so this gives you a basic first step, but there are natural further questions. I'm going to try and stick to writing in the light. Well, the most natural one, of course, is how is this normalized number distributed in this interval? I mean that I'm not even presupposing that it even has a natural distribution, but you might guess, and you can certainly take polynomials and compute and see what type of graphs that you get. And this is, in fact, a very rich question. It leads to various very natural conjectures, such as the Sato-Tate conjecture, and many generalizations of that. But I want to just even stick with an even more basic question. So, I mean, if we can't answer this question, maybe we shouldn't be allowed to think about this question. Okay, so the question is, well, first again, I want to assume that my polynomial is at least 3, it has degree at least 3, because the other cases are trivial. And then I could ask, do there exist infinitely many primes such that what? Well, here I have this number varying in this interval. So the most basic question you might ask is, for example, such that AP is positive. Okay. And perhaps surprisingly, this is completely open. And when I mean completely open, I don't mean that there aren't some cases that are not known, but just for a general polynomial of high degree, we really have no idea how to answer this question. Okay. So, for those of you who are experts, I'm soon going to just tell you a few results in small degree. What I've left as a challenge problem, maybe for Noam, if he's here, is can you even find a single polynomial, f of x, of degree at least 3, without repeated roots, so that you can prove this, so you can answer this question in the positive in an elementary way. And when I mean elementary way, I mean not using automorphic forms. Okay. Okay. So here's a theorem. The answer is yes if the degree is equal to 3. Or, of course, the analogous question when d is equal to 4. So who proved this theorem? Well, it's rather a corollary of results of other people. It's a corollary of a theorem of Wiles, Taylor-Wiles, and Breuil, Conrad, Diamond, and Taylor. So these group of people in the sequence of works in 95 and 2001, they proved another seemingly different sounding statement, namely that all elliptic curves over Q are modular. But one consequence of that result is this theorem. And I believe, although I'm not 100% certain, is that it's very hard to even answer this question without a theorem of somewhat of this strength. Well, in the case of a CM elliptic curve, it's also a theorem, maybe of Hecke. But using Hecke to solve that problem, that counts as using automorphic forms, so you're not allowed to do that. Okay. Okay. So here's another theorem. The answer is still yes if the degree is equal to 5 or d is equal to 6. And now this is a theorem that, in part, I'm talking about today with George Boxer, myself, Toby G., and Vincent Piloni. Okay. So what's going on? So this is seemingly elementary problem, but apparently wrapped up with something more complicated. So in order to try to answer this question, I want to take a step back, or rather take many steps back, and just try to explain what is algebraic number theory. And from that, why are we led to the question, perhaps, of counting solutions to equations mod p, and what, hopefully, does that tell us about the questions we're interested in? Okay, so what is algebraic number theory? So one answer is it's the study of algebraic varieties over Q. Or in other words, it's the study of polynomial equations with coefficients that are given by rational numbers. Okay, well, let me just write down examples of systems of polynomial equations in rational numbers that were studied historically. One was x squared minus 2. So this was studied by the Greeks, who determined that it didn't have any rational solutions. Another type of polynomial equation is, say, the equation was x squared minus 2 is equal to 0. Another equation is x to the 5 minus x minus 1 equals 0. This was studied by Galois, who proved that equations of this form, and in fact of a general form, can't be solved in terms of radicals. Let me write down another equation. Say x to the p plus y to the p is equal to z to the p. So if I think of these variables as projective variables, this gives me a nice projective algebraic curve. Okay, so we write down these equations, and then what do we want to say about them? Well, there's many natural things, but of course the first natural question is, do they have rational solutions? But that's not the only question in algebraic number theory. We might be interested, for example, in knowing when one set of equations is equivalent to another set of equations by some natural notion of equivalence. So in other words, we might be interested in the kind of classification problem. Okay. So the first principle in algebraic number theory that you learn about is that even if the questions you're interested in, of course, by their very nature, have an algebraic flavor, geometry is never lurking far from the surface. And that comes up in many forms, but perhaps one of those most dramatic versions of that is in the conjecture of Mordell, or the theorem of faultings. So let me just give this an example. So say I have x over q. Well, let me just say an algebraic curve. And maybe let me even add, I can always reduce in this case, smooth and proper. But you should just think, suppose I give you a single polynomial equation in 3 variables that's homogeneous, or maybe 2 variables that's not homogeneous, and then I look at the solutions to that polynomial equation. So of course we're interested in the solutions of the rational numbers, but we can look at xc, which is the set of complex solutions. And in this case, the set of complex solutions, embedded, for example, in some projective space, in fact has a nice topological or even geometric description. It automatically is going to be a compact, orientable surface. Of course, it has extra structure, but it's certainly this. Now, in fact, such surfaces are either given by spheres or curves of genus 1, genus 2, etc. They're essentially determined topologically by some number g. So for example, if I took a plane curve of degree d, for example, this is a plane curve of degree p, then the formula for g, as it is in this case, would be p minus 1 times p minus 2 on 2. All right, so this is a geometric object, and then the theorem of faulting, so conjecture of Mordell, says that if the genus is strictly bigger than 1, then the number of points of x over q is finite. So it's a very beautiful theorem, but perhaps in the context of why I'm bringing it up here, is it just very clearly delineates that the geometry of what's going on is highly related to the arithmetic. And that's somehow a principle that is always occurring in this area. Okay. So, therefore, if we want to understand everything about algebraic number theory, step 1 is understand everything about algebraic geometry over the complex numbers. Okay, so let's do that. And so let's suppose we want to understand these algebraic varieties where we're now thinking about them in terms of their complex solutions. Okay, so how do you understand topology? So the basic principle of geometry is that geometry is difficult to understand because it's nonlinear. That basically there are only two things we can do in mathematics. One is linear algebra, and one is combinatorics. So if we want to understand a structure geometrically, we need to give some linear algebra or some combinatorial structure to this. So what's a natural way of having linear algebra? Well, if you think of something geometric, the natural way of having linear algebra associated to that is to look at a tangent space, which is something that has a linear structure. And more generally, associated to a variety, we can look at the cohomology of this variety. And let's, for now, think about coefficients in Q. Okay. So, all right, if you're a topologist and you're trying to understand the cohomology of a variety, well, you have some classes and you want to say, well, how do I understand what a cohomology class means? So one natural way to think of a cohomology class is to represent it by sub-manifold of your original manifold. If I'm thinking of a torus, its H1 is given by two copies of Q, but I can think of these copies of Q as generated by a meridian or a longitude as little loops around my torus. So the question is, can we do the same here? Well, what would that mean? We'd be looking for subvarieties, but of course we don't just want any subvarieties, we want some kind of algebraic subvarieties. So you might hope, well, can you explain all of this cohomology in terms of algebraic subvarieties? And what you quickly realize is, well, there's going to be an obstruction to doing so, because if I have an algebraic subvariety of this, then when I take its complex points, because C has two real dimensions, I'll get a variety of a submanifold of even dimension, and I'll only be able to see cohomology in even degree. Okay. Well, all right, so perhaps you might just ask, well, can I understand the cohomology in even degree? So how might one try to do this? Well, in fact, associated to X, I can try and imagine maybe just the free Abelian group generated by subvarieties of codimension I, and then, essentially by taking the corresponding class, give myself a map which will now be in even degree. So I can get a map of this shape where somehow, here I'm thinking the image is things represented exactly by these algebraic subvarieties. So now you could ask, well, maybe this is surjective. And again, that turns out not to be the case for a slightly more subtle reason than for odd and even dimensional, but still for a kind of explainable reason. And maybe to explain it, I first have to give an example of a complex variety that's coming from an algebraic variety. And so my favorite example of this is just to talk about a curve of genus 1, which when you think about it as a complex manifold is just a torus. It's C modulo a lattice. So the complex points of an elliptic curve are given by C mod a lattice. Okay, so this has cohomology in degree 1, as I just explained. It's cohomology is two-dimensional. Okay. But in fact, if we give ourselves the right to enlarge the coefficients, we can replace this description of cohomology by a different description of cohomology. Namely, we can look at the de Rham cohomology of xc with coefficients in R. So de Rham's theorem says that if you take a form you can integrate, you can pair it against loops, you get a perfect pairing, you get an identification between the de Rham cohomology and the usual cohomology if I had coefficients over R. So by increasing this to coefficients on R, I certainly have an isomorphism like this. But moreover, this is very easy to describe in this case. Here I'm just looking at forms that I can integrate on C mod lambda. So I can pull them back to C, and so I have some one forms that I can integrate on C, which is basically R squared. And so I have a description of H1 de Rham with coefficients in R as just generated by dx and dy. These are nice things you can integrate, and they're also invariant under translation, which exactly means that they give you classes on here. Okay. But now, so far we haven't used the fact that this is actually coming from a complex variety, and the fact it comes from a complex variety actually gives the de Rham cohomology extra structure. Namely, that if we allow ourselves increasing coefficients once more to have coefficients over C, this is still a two-dimensional space, but it has a canonical one-dimensional subspace. There's a particularly nice differential inside here, namely the holomorphic differential dz is dx plus I dy. Now there's also an anti-holomorphic differential dx is dx minus I dy. And so what's coming from these algebraic varieties that secretly have this complex structure is that their de Rham cohomology has this nice decomposition into these forms here, at least for H1, into holomorphic and anti-holomorphic forms. And more generally, Hn will have a decomposition into a set of spaces HPQ, where P plus Q is equal to N. And classes in there, well, they're realized essentially by harmonic functions times differentials of the form dz1, dz2, up to dzp, where dz bar p plus 1, up to dz par p plus q. Okay. So to give one example, if I take H2, now, again, just of this torus, well, of course, H2, I can get it by taking dx wedge dy, but I can also take it in just the same variables as dz wedge dz bar. So in fact, this case, it's equal to H1, 1, is this decomposition. And so what happens, in fact, if you take a cocycle, if you take an algebraic subvariety and look at the corresponding map, essentially the algebraic nature of this will give you a restriction on the image of the class, namely that it will always land inside in degree h to I. It will always, in fact, land inside the intersection of that with hii. Okay. And so one thing that's important about this description here is that here, this is a rational vector space. But this filtration here doesn't exist on the rational level in general. Rather, to obtain it, I have to tensor up with C, and then C, in that, over C, it has this extra filtration where I can start to exploit this. So in particular, even if this is non-trivial, there's no reason why this intersection has to be trivial, or non-trivial. I mean, of course, if it's everything, then it's certainly the case. All right, so then we have the minimalist conjecture. Is that is surjective. I mean, this is what you do in mathematics. First, you assume it's surjective. Then you find a reason why it's not. And then you say it's surjective onto the things that you can't prove it's not surjective. And you keep going until you can't prove it either way. And so this has a name. This is called the Hodge conjecture. And what it somehow tells you is that, perhaps surprisingly, I mean, if I take these elliptic curves, I mean, often you'll see you have many algebraic varieties which their cohomology, just as vector spaces, is not so interesting. It just tells you something about the dimension. But they secretly have this extra Hodge filtration that maybe is telling you something more rich about various cycles and subvarieties. Now, put it that way, that's a little, I think, recherche. And I want to say a little bit more about why actually this goes a long way, at least if you're willing to squint, to answering the question, how can we tell when algebraic varieties are the same? I mean, we're interested in some classification problem. Here I'm giving you something peculiar about some weird subset which is coming from some kind of subvarieties. So the main reason, well, one main reason for thinking about that is to try and ask when are two algebraic varieties the same, or even two complex algebraic varieties. So maybe we have an x and a y, and we want to ask if they're the same. Well, of course, the first requirement is that their cohomologies must be isomorphic. But if they're really also the same as complex algebraic varieties, then not only is their cohomology isomorphic, but the corresponding filtrations on the Durand cohomology are also the same. And so we get something stronger, not just an isomorphism of vector spaces, but some extra structure, some isomorphism of Hodge structures. So why is that good? Well, now the secret, let me just suppose that the dimension of x is equal to the dimension of y is equal to d. So now I want to look at the cohomology in degree d of x times y. Okay, let me kind of leave out the coefficients. So by the Kunneth formula, the cohomology of x times y in degree 2d sees the cohomology of x tensor the cohomology of y. And now if we really assume that not only are these vector spaces the same, but the corresponding Hodge structures are the same, then in fact we could deduce inside this tensor product that there are some classes which lie inside HDD. And so if we give ourselves the Hodge conjecture, we get some cycle inside x times y. They both have, some cycle inside x times y of codimension d. So they both have dimension d, so it has codimension d, that explains why this cohomology is the same. So what's kind of the best possible example of such a cycle? Well, of course, I can have a map from x to y that's an isomorphism. If I have such an isomorphism, what is the corresponding cycle? Well, if you've taught calculus, you can just write here x, y, and I just write the graph of this function, and that will be a cocycle of the correct dimension. And this cocycle, which is isomorphism from x to I, is what is explaining why the Hodge structures are the same. Now, unfortunately, the Hodge conjecture isn't quite strong enough to really tell you that x and y should be the same. I mean, maybe that's fortunate because it's not true in general, but it at least tells you that there's geometric reasons for why the cohomology is the same. And really, if they're not literally the same, for many purposes, they're quite similar. And so one thing that might suggest is, well, maybe studying algebraic varieties is hard, but Hodge structures, well, that's just linear algebra. I have some vector space over Q, maybe which has a filtration over C with some extra properties. That's much more algebraic. That's much more linear algebra. Perhaps by understanding that, I can say things that are sort of inaccessible by geometric means. I apologize for the squeakiness of this. Okay. Well, let's now return actually to thinking about algebraic varieties of a Q, which is really kind of what we're most interested in. So it turns out that there's a similar story one can do is instead of looking at de Rham cohomology, I can look at the so-called étale cohomology groups. So I have to make a bunch of auxiliary choices, maybe a choice of prime L, maybe pass from X to X over the algebraic closure. But I have a sequence of vector spaces that you should think as very similar to what I had before. Namely, just as a vector space, it has not much information, namely just has the dimension. But over here, I had this secret filtration going on. And here I have an extra structure, namely the action of the Galois group of Q. So this is just the Galois group of Q bar on Q. That's just the inverse limit of the Galois group of every single finite extension. So in other words, the symmetries of all algebraic numbers. Well, there's no Hodge conjecture per se for étale cohomology, but there is an analog called the Tate conjecture. And again, it says something very similar. It says that if the cohomology groups you get with this extra structure are the same, it should be explained by geometric reasons. So étale cohomology groups are a little bit hard to motivate in terms of their definition. So instead, let me kind of say something that you can get from these numbers or that you can get from X. If I take my system of polynomial equations, one thing I could get, at least for all but finitely many primes, is I can reduce the equations modulo P, and then I get the solutions over Fp, which will be a finite set, and then I get some sequence of numbers which are just the number of solutions to this equation. Okay. So what you should roughly think, and this is essentially true, is that these two pieces of data are the same. In other words, from this étale cohomology, you can count the number of points, but also from the number of points, if it happens to have come from a Galois representation, it really determines it, at least up to semi-simplification. So the analog now of this Hodge conjecture, which becomes the Tate conjecture, now it says if I take two varieties and they have the same number of points mod P, then, well, perhaps they're not exactly the same, but they're highly related, and that the reason they have the same number of points mod P is for some geometric reason. Okay. So I'd like to draw the following cartoon just to summarize this. So the middle bubble is going to consist of algebraic varieties over Q. Okay. And so what I've said is that from these varieties, you can collect some sequence of numbers which are just the number of points that X has over Fp. So some sequence of numbers. And so the Tate conjecture says that the kernel, to the extent that this has a kernel, this is not really a map of things that is an Abelian variety, Abelian category. What do you leave out here? What's missing here? Well, I was basically trying to sell this as corresponding either to de Rham cohomology or étale cohomology. This you should think of as being linear algebra. So that must mean that the kernel is combinatorics. Okay, and so here's just an example. I can write down some very simple varieties that have the same number of points, mod P, but aren't different. So here's an example. I could take just 3 P1s going through a point, or I could take 3 P1s which intersect at different points, and they both have the same number of points mod P because they each have the number of points that P1 has times 3. Well, then I have to subtract off, oops, I drew the wrong picture. I have to subtract off 2 points. So maybe I'd want to draw this picture like this. Okay. So they have the same number of points mod P, and of course they're not the same. But you might imagine that they're kind of built out of the same object, namely P1 in some combinatorial way. And so what's interesting or difficult about an object here is really about combinatorics and gluing things together, rather, for example, than something to do with the corresponding Galois representations. Okay. And so I kind of break up, if you're an algebraic number theorist or an arithmetic geometer, you're much interested in kind of the image here. And maybe if you're kind of an algebraic combinatorics, you're sort of much interested in this picture here. So I favor neither one nor the other. All right, so why did I want to kind of do this fairly long detour? Because what I want to justify from this picture is that this map here, its image is very rich. That from this data, you should be able to extract a lot of information about X. So when number theorists start doing weird things like counting points, I mean, at least if you believe the Tate conjecture, then they could honestly say they're really studying motives, they're really studying algebraic geometry in a genuine way, and they're not just sort of doing something maybe a little bit silly. But more importantly from that, what we now want to do, I mean, of course, the challenge, maybe we can't prove the Tate conjecture, but what we like to do is extract from these numbers information about X. I mean, theoretically, it should contain all the information about X that you maybe, except that you can, maybe by sort of gluing and combinatorics, you can't see. Okay. So that's where we go next. Okay. All right, so it turns out to be useful to remember not just the number of points X has over a finite field, but maybe the number of points it has over all finite fields, so extensions of FP. In fact, that number can be extracted from here in some very loose sense. It's certainly determined by this, but for the next thing, I might as well give myself these numbers. Okay. So given our X, we can form the following kind of strange expression, I think, when you first see it, which is a generating function for the number of points of fp to the k times p to the k divided by k. Okay. So you might ask, why considering this generating function rather than just the sum xp to the k times t to the k? And the answer, like it is often in mathematics, is because it works. And so a remarkable fact, it's a part of the Weil conjecture, as I mentioned before, is that this, which I can just define to be the zeta function of f over fp, is actually a rational function, but even a rational function with rational coefficients. Okay. So, example, let me do the case of x is a point. Then all these numbers are 1. You recognize this as basically minus log of 1 minus t. And so the corresponding zeta function in this case is 1 on 1 minus t. Okay. So even getting this far for algebraic varieties of a finite field is a non-trivial task. But now let's raise the stakes and take all primes at once. And again, I want to make the following construction. So now I have all primes. And for each prime, well, I have to worry a bit for a few small primes, but I'll just ignore that issue. I can take this zeta function, and I can plug in p to the power of minus s. Okay. So again, let me continue on with the same example. If I do a point, I get the following product, the product of 1 on 1 minus 1 on p to the s. And as was well known to Euler, this is equal to the Riemann zeta function, which is the sum of 1 on n to the s. And again, you could argue this is a strange thing to do, but somehow remarkably what happens is that whatever variety x you choose, when you do this somewhat peculiar construction, you get, at least conjecturally, a function with some amazing properties. Okay. So even just stopping here for now, you could ask yourself the question I had before, which is that in this map, I go from a point, I get the point counts 1, and then I get this Riemann zeta function, and so what can I start extracting about my point? What information about my point can I extract from this number? Well, because as analytical continuation, I could say evaluate it at 0. And if you evaluate at 0, you get minus a half. Or if you use the class number formula, you deduce from that that the class number of Q is 1, or namely that Z has unique factorization. Okay, so that's some information included inside a point. Okay, so now the question is, what happens if I start taking a more general I think it may be a hard way, but I believe it is actually a genuinely different way. I don't think that proof uses. Oh, maybe it does. Well, no, maybe, no, I think it doesn't. Yeah, no, I think that does give you a proof. Yeah, no, of course it does. All right, so what could we hope if we take a general variety to expect about this function? So let me assume x on q. Let me now just assume it's proper smooth over q. That's just removing singularities. That's just easier to say it in this way. It's not really necessary, but I just prefer to do this. Okay, so then we have the following conjecture, which is called the Hasse-Weil conjecture. Okay, so part one is when I take this corresponding function, it has a meromorphic continuation to all of C. So already in the case of a point, what this is relating to is Riemann's proof that the zeta function has an analytical continuation. Well, of course, the Riemann zeta function has not just an analytical continuation, it also has a functional equation, and that's part of this conjecture too. So part two is that there exists a rational number A. In this construction, I was a little bit uncareful about what happens for small primes, so we have to be a bit careful for small primes. So some polynomials, Q, L, T, for primes dividing S, which is maybe just the set of bad denominators in my original thing, and a gamma function, a gamma factor at infinity. This will literally just be given by a product of gamma of S or gamma of S on 2 shifted along the real line by some finite amount. So with these two together, I can form the corresponding completed L function, which I hopefully know how to do. S, I can multiply by this power of A to some power of S. I can multiply by this gamma function. And then I can also include these bad primes and put in the correct Euler factors here that maybe were done incorrectly because maybe I was looking instead of the equation x to the p plus y to the p is z to the p, I was looking at 7x to the p plus 7y to the p is 7z to the p, and I'd have the wrong number of solutions mod 7. Okay, so I adjust this, and let me also, to avoid trivialities, assume I didn't choose any of these functions to be 0. Okay. So then this has a functional equation exactly like the Riemann zeta function, but now it's shifted by m instead of m plus 1 by instead of 1, where m is the dimension. Did I miss the chalk? Yeah. Okay. All right, so for example, this conjecture is known for a point. But to some extent, not so much is known about this conjecture. I want to say a few things about it and some new results, and then I want to connect it back with the problem I gave originally. So let's maybe instead of thinking about all algebraic varieties, let's concentrate on the case of curves. So let's assume x on q is a curve, and then it comes with some genus, which is just describing what the complex points look topologically. So in this case, you can actually write this zeta function in terms of the usual Riemann zeta function, like we had before, shifted by 1, and then divided by something that only depends on the first Étale cohomology of x, maybe with some chosen coefficients. Okay. So what do I mean by this? Well, this is some Galois representation of dimension 2G, and associated to this, and I'll make it more explicit in this lecture, we can also associate some L function, and then we just factor it in this way, corresponding essentially to the fact that the zeta functions over finite fields look very much like 1 minus t, corresponding to here, 1 minus pt, corresponding to this, divided by some polynomial of degree 2g. Okay. So now we have the following theorem. So this is due to Riemann in 1859, again, somewhat anachronistically. So if g is equal to 0, then the Hasse-Weil conjecture is true. Because namely, in this case, this factor disappears. You just end up with the Riemann zeta function again, and it follows from Riemann's result. And now, to return to the theorem of Wiles, Taylor-Wiles from 95, and Breuil-Conrad-Diamond-Taylor from 2001, if g equals 1, then the Hasse-Weil conjecture is also true. So I should say that they prove something stronger. Namely, they not only proved that this function was meromorphic, they proved that the denominator was holomorphic. If I take a ratio of holomorphic functions, it's meromorphic. But it's not true that even for genus 1, this will not be a holomorphic function. This ratio, if you believe the generalized Riemann hypothesis, this will have lots of zeros. That should have been in so it should have really been S. This has lots of zeros where the numerator doesn't have any zeros. And so this will in general have many poles, even provably in many cases. So even though they prove something stronger about this function in the context of the Hasse-Weil conjecture, they don't prove anything more. And then the theorem, well, one version of the theorem that we proved, well, you can probably guess. If g is equal to 2, then the Hasse-Weil conjecture is true. Okay. And I always like to summarize, I know this is a little facetious, I like to summarize the result thus. If you remember nothing from this talk, think Riemann, Wiles, and then us. Okay. So in the last 2 minutes, I just want to say, what type of information can you extract from this? Well, let's even go back to the Riemann zeta function. So here I was talking about arithmetic applications, namely, I could deduce from the special value of 0 that z had unique factorization. But if you ask a random person on the street, well, maybe a random person on the street in Cambridge, what information do you get from the Riemann zeta function and its functional equation? They would probably tell you, well, you can deduce that if I take the sum of 1 for the number of primes less than x, I get x mod log x. In other words, the prime number theorem. And so, in fact, in this case here too, by using either the Hasse-Weil conjecture or in fact something a little stronger that we actually prove, we can also deduce results of this nature for corresponding things involving how many points a curve has mod p. So now let's go back and think about the equation y squared is equal to f of x. So this is a curve which, if the degree is 4 or 3 or 4, it's a curve of genus 1. If it's 5 or 6, then it has genus 2. And if I count the number of points, well, how many points does it have? Well, there's always a secret point at infinity. And then, well, each time this is a square, I get 2 points. If it's a non-zero square, I get 2 points. If it's a zero square, I get 1 point. If it's not a square, I get 0 points. And so this is exactly equal to 1 plus p plus this number AP that I was talking about before. And then an analog of this result, say by the prime number theorem, when you plug it into the functions you have here, you get a corresponding prime number theorem for these numbers AP, namely that you get the sum of p less than x of AP. Well, let me now normalize it by dividing by the number of primes. So if this was just 1, then I should get 1. And also, let me also normalize this number by dividing by root p, so this guy is always inside some bounded interval minus 2 to 2. So one thing you can deduce is that this is actually converging to 0. And by thinking about a slightly different version of an L function, which you also have access to by this result, you can also deduce that the sum of p less than x of not this quantity, which is between minus 2g and 2g, but rather this quantity squared, is converging to some integer which is bigger than 0. And now from these two prime number theorem results, we basically, these are numbers between minus 2 and 2, or minus 4 and 4. And if they're all positive, well, x is basically bigger than x squared up to a constant. So if this is going to something non-zero, and all these numbers are positive, this also has to be non-zero. And so you, in fact, deduce from this analytic argument, which is a prime number version, that this has to be positive, and also by the same argument, negative half the time. Okay, so in the next talk, I'll say a little bit more about some secret objects in the background, and maybe even a few hints about some arguments.